me just, and then share screen. All right, so I'll get the video from this and I'll put it in YouTube and post to YouTube. The page is that's running. See, so the web page is this. So if you like what I did when I first came in, I typed in just my name, Beaucage. And then one of them is like Beaucage Research Group. Used to be the top one, now it's like something else. So I'm losing out. Anyway, so if you find that and click on that, and then this class, these are like all the classes, most of the classes I've taught, you know, so there's a ton of them, but basically the Polymer Physics one here on the left-hand side. You can look at the other ones too if you want, but and then so anyway, that takes you here, and then I'm gonna, all right, so this used to be a much more kind of junky web page, so I took all the junky stuff and I put them into separate cleaning up things, so kind of boxes. Eventually there'll be like so many boxes, I can make a box for the boxes, you know. But anyway, so the old, like all the old class videos, so I taught this for a while, so there's like a bunch of old class videos that should work. And then these things will be like some video from 2019, yes. So it's kind of weird because I moved it to a folder somewhere, so I had to change all the links too. But you can do that all at once, so it's not as hard as it looks. But then so every week we'll have like a paper that we'll go through. So it's like 19 undergrads and I think whatever to 31 grads. So it's kind of, it's a grad class, but it's kind of like populated by undergrads. So anyway, the undergrads, it's the same, everyone will be like treated the same, but basically undergrads get a 1 grade boost. And the other thing is if you're a senior in the, if you're a senior graduating this semester, then you don't have to do the final, which is going to be another kind of homework paper thing. That's worth 5 grades, 5 of the other grades. So, I mean, you can't do it if you want, like if you need to or something. You know, basically you don't need to. Probably none of you will do it. But so the reason to do it is because it's for the PhD, they have to do a qualifier, and it's kind of like an example qualifier. They can kind of get a practice in on it. And then, so it's kind of like, so basically, let's see, so that's the logistics of it. So every week, I'll sign it on Friday, so I'll put it up on Thursday. You'll know where, so anyway, I put everybody into the undergrad thing because there were 19 there, so I could just do an automatic group thing there. And so I moved the grads into the undergrad, and that grads, you should have gotten an email that said like, you want to join this other class? So you should just say yes, and then you're in that thing. Then you should be able to access it theoretically. Hopefully that'll work. Otherwise, in the past, I've made like an Excel sheet and I put everyone in it, and then you had to figure out what group you're in and stuff. So anyway, the idea is to mix it up so you get different people every week, and the hope is that you get at least 1 grad mixed with 2 undergrads. But since I did it randomly, that's not guaranteed. So if it's all undergrads, maybe if you feel like you need a booster or something, let me know. Just tell me it's like, oh, we're all undergrads. Because otherwise, yeah, it'll be hard to keep track of it. Anyway, so that's the logistics. So it's just like a homework a week. That's it. And then this final homework, which is like a mega homework. It's like 2 homeworks, but you have 2 weeks to do it for the grads. Anyway, so that's the logistics of the thing. Hopefully that'll work out. I mean, in the past, I've done like a quiz a week, which is like harder than the homework a week. And so on Friday, so I'll put this thing up on Thursday, most likely. Then on Friday, I'll kind of go through a paper, like whatever I'm talking about that week. And then I'll kind of go through the questions on the homework and kind of answer them for you, but you may or may not be able to understand it. You know, so it may or may not help to have the answers. Right. So the idea is that you can kind of get a view of kind of what's going on like right now. And hopefully the papers will be from like this kind of this year or last year. This is something recent where people can how people are using things. So to keep it kind of current, because things tend to get stale, you know, and it's better to have people have different opinions about things now than they used to have, so things change. So it's good to have this kind of current thing on it. And it also, it broadens the scope too to different things. So anyway, what I'm going to cover, I was messing around with this, and the PDF links all work, so it's almost like you want to use PDF in this thing. But then on the PowerPoint, I have a hard time with the links working. So anyway, this is kind of what. Well, why don't I just run the PowerPoint though, since this thing is going to be diplomatic. There's one link I want to go to, but okay. Here. Everything takes a while to boot up the first day of the semester. For some reason, it's a lot of questions. Let me hide this thing. So if you do the Zoom thing, like I don't usually look at the oh, there's already one person there. So I don't usually look at the chat thing. So just come in with your voice, like just scream something like, hey, anything, it doesn't matter. So if and the more interruptions, the better, because it'll slow down the pace of things. So it'd be good to kind of get as many questions we can get on stuff, And then, and there's no real fixed amount of stuff we need to cover in here. And also, so if there's some things, like if you're doing a co-op job and you're interested in some particular area, polyolefins or something, then let me know and I can cover more of that. Whatever it is, coatings, whatever. So anyway, but generally, like this is the kind of the description of what's going on. So you have usually so basically polymers or plastics is kind of divided into 3 fields more or less. So basically chemistry. So if you take like Neil Ayer's course in chemistry is polymer chemistry, it's just synthetic chemistry more or less. Then a little bit of polymer physics too. Then Judiro's class is kind of a mixture of everything. So it's kind of like chemistry, and then there's kind of physics thing, and then there's like kind of a engineering, mechanics, rheology part. So it's kind of 3 tiers to it, like a stool. And there's kind of people, so people aren't experts in all 3 usually. Although people try to pretend that they know some chemistry, and you get by with like rudimentary chemistry, like solid gel chemistry or condensation stuff. So there's some chemistry that's so simple that you don't even need to know what you're doing. So with a nylon rope trick or something, pretty simple to do. So although toxic, but anyway, I used to do that trick in class, and I found out that the polyamine, whatever, diamine, that thing's a tetragen, a carcinogen. It's like every other kind of total poison, So anyway, I didn't do that anymore, but it's kind of fun. I mean, maybe you've seen it before. Anyway, so anyway, yeah. So chemistry is one area, and then physics is like the other area of polymers, and it basically because Paul Flory was a guy. Actually, he got a PhD from Ohio State, and he taught at UC for a while, and then he went to Goodyear, and then DuPont, and then Columbia, and then Stanford, and won the Nobel Prize. It's like he was kind of like the father, more or less, of U.S. polymer science stuff. So he was a physical chemist, so that's why it's like physics and chemistry in a sense, And he wasn't really a rheologist, but most of the work, like when you go into industry, it's going to be all rheology. Basically, everything is like making something, so you're going to be extruding it, right? So basically, injection molding, extrusion, like wire coating, stuff like that. So all those things are basically rheology, meaning flow, right? So not Newtonian rheology. So if you go into industry, that's like the most important thing is a rheology, basically. And the physics a little bit, and the chemistry somewhat too. So basically, anyway, so we'll cover some rheology, but basically the traditional way to do this course, which is based originally in Flory's book called Polymer Chemistry, is to start out with this kind of description of an isolated chain, just called basically the single chain kind of statistics, and then go into how the chains interact with each other, which is this long range interaction thing. And then basically the rest of the thing is kind of talking about different analytic techniques in here, I mean, this is like more or less how the course is set up. But then I've added in a section on like machine learning and some stuff on recycling. So there's a few other things I've thrown in that we may or may not cover, you know, we don't need to, but we can. It depends on, again, like what you guys are interested in. So if you're doing like co-op job in some area, you want to know more about that, then I can put that in here. Anyway, so yeah, this is the web page for this. The class, you want to write it down, or you can just kind of follow through it that way. And then that's the Zoom link for this. I'm not sure I posted that on the web page. Let's see if I did or not. Let me see. Yeah, I'll put the Zoom link up here. I'm not sure why it's not there. Yeah, it's not here. So basically, I'll put the Zoom link there. Or you can open the slides one, like the PDF will take you to, and the Zoom link is there. So you can do that if you want. But I'll put it up there if I remember. But anyway, so yeah. So that's kind of the scheme of the way this thing goes. So any questions on that business or anything on so the groups will like rotate and they're all set up already in the is it canopy or canvas?
Canvas.
Okay, because it's the thing I go to when I sign in, I go to canopy and I go to canvas, so I never know which one. Anyway, yeah, canvas. So it's in there, it's all set up, it should be fine. Then the homeworks will be posted on the web page. So it'll be like let's see. In fact, like if you want to see, let me see. There. So there's all the old homeworks and stuff I piled. See, this was originally on the other web page, so it's kind of like a million things. So originally we did quizzes every week. Then I went to this homework format. I guess it seems like I look back, it's probably around COVID, you know, that I went into this homework thing. Kind of like to take a paper and just go through it. Anyway, it seems all right. It seems to be a pretty good way to do this stuff. So the old ones are here. Like the last year's. This is a good one. I kind of tempted to redo that one because it's about polymer crystals and the crystal theory stuff. It's like the homework will be there. Then I'll be talking about some paper. That's a long homework. I mean, long text in it. And then there's some papers. This isn't a new paper. It's like from the 60s, right? Like one of the original polymer crystal things. And there's some other papers. These are more recent, I guess. This was like the year I signed the thing. So basically, there'll be a few things to look at. So you have to kind of digest that. So right now it's set up like I'll put this up on Thursday, and then Friday I'll go through it, and then it's basically due on Monday at noon. Let's see, no, do it Sunday at noon. So that seems like it's too short, I guess, when you think about it. The nice thing is I can go through the homework on Monday, like after grading it. The disadvantage is not enough time. So if you guys, anyway, you can always write. Like if you say like, oh, I need more time, I'm gonna just say, okay. It doesn't matter that much. So basically, let's try it this week with the Sunday at noon due thing. And then if it's like a problem, let me know, and maybe I'll move it to some other.
So you'll post it on Thursday and it'll be due Sunday?
Yes, at noon.
Can you push it till midnight?
Yes. Whatever you ask, I will say yes. So, but basically, it's to your disadvantage to keep pushing it back. Because there'll be another one the next week.
Noon is just a weird deadline.
Yeah, it's kind of weird.
It's just more convenient to go to the entire day of Sunday.
Yeah, but then I can grade it Sunday night.
That's
So that's why I said noon. If I get a few of them at noon, then I can grade some of them and I can at least see, like, are you dying on this thing? Or are you surviving through it? So so on Monday I can go back and say like, oh, you all died. Here's the way to redeem yourself, whatever. But so I guess I wouldn't worry too much about the grades. And the idea of the group thing is that, all right, so there's always one person that's better than the others. And there's always like one person doesn't want to do anything or has something else to do or whatever. So, but the original idea was that, yeah, this one person's better, but they can kind of teach the other people, especially if there's a grad student, two undergrads. They could have, well, the grad student's kind of responsible for it because they're more interested in like passing a qualifier than like the undergrads can kind of be trained by the grad or whatever. Or the smart undergrad can train the grad too. That happens a lot. I mean, sometimes. So anyway, whatever. I mean, if you're thinking about going to grad school, you're undergrad and thinking of going to grad school, this is a pretty good course to take for that because it basically you would already have a pretty good background. And I can write you a letter and stuff too, so that helps. I mean, so anyway, if you're just going to go work, then I'm going to try to cover rheology and stuff, and you'll hear this stuff come up. If you're at a larger company, you know, you'll hear the subjects come up, and you'll kind of can show off that you know something. You know, so I think there's some advantage. If you're a small company, the merit of it becomes less, you know, because there won't be any expert polymer person there. But you may have people that you're contracting with that, so it will help at some point. I think if you stick in the polymer field, which is it's a good field to work in, but not really going to go away soon, despite all the dire warnings. But and in fact, there's more and more work because of the dire warnings. It's like people are really working to find cyclic economy polymers, and there's a lot of problems to deal with. So so it's a pretty good field. It's been a good field for a long time, and it's going to be a good field for a while in terms of industry. In research, it's pretty active. You know, it's not as active as like batteries or something, you know, where there's a lot of big impact for small changes. Like you can change the anode on a battery to be 10 times better, then all of a sudden, like electric cars become a lot more tangible. You know, so whereas if you make a better polymer, basically you're not going to industrially, unless it's some huge thing, you know. I mean, you're not going to make a new polyethylene, you know, because basically the entire world is running on polyethylene, you know, so every extruder, so it's a whole sequence of companies like the Lyondell, and Cincinnati has all these companies here, like Lyondell's this top manufacturer of polyethylene, polypropylene in the world. And then Procter & Gamble is one of the biggest consumers of, and then all the spin-off companies from Procter & Gamble, like there's a lot of film extruder companies and like the wire and coating companies in Kentucky, General Wire or whatever it is. But so anyway, and we have two extruder companies like Cincinnati Millicron and Krauss-Maffei's across the river. It's like the two major polymer extruder companies are here. So basically, Cincinnati's a pretty big polymer base in terms of industry. So basically, we have kind of all the components of it here. So it's kind of interesting. So maybe we could even maybe we could tour, like at least Lyondell, we can definitely tour. Like we can go look at their labs and stuff if people are interested. It's not a big deal to do that. The biggest deal is like finding a time to do that. But we can do the same. P&G's plastics divisions on like Winton Hill, I think. They haven't moved it. So we can go up there probably and look around. So they're kind of secretive because they have like designs of bottles or something there. It's actually harder to get a tour of their place. But it's possible. I mean, I know people there, so we could probably do that. And maybe some of you guys know people too, if you go up there. And what else? The extruder companies we can definitely tour. So that's kind of interesting too. So basically, if you guys want to do tours of places, there's a bunch here to look at. Probably the Lyondell's the best, you know, because it's got a whole like analytic lab full of all different kinds of and big full scale film blowing machines and things, like 3-story machines to make garbage bags, basically. So anyway, so all right, so we can do that if you want. You can add that in. But anyway, so let me see if I can hide this thing. All right, so yeah, so the old homeworks are here if you have it. So if you're going to take the qualifier, maybe you'd want to like fish through some of these and see, because it's basically the same thing as a qualifier, like give a paper, say something about it, type thing, answer 5 questions. So if you say you did like, yeah, PhD. So when you take a PhD, you have to do a qualifier first. So your first year, you take classes, and then kind of at the end of that, generally you like take an exam. So like a cumulative exam in whatever subject area you want to work in. So if you're going to work in polymers, you take this exam. So it's pretty similar to the homework. So if you're thinking about grad school, it might be good to look at that if you want. But anyway, that's kind of how we do it for the time being. But so okay, that's about it. So is that, hopefully that'll work out. If it's not, if it like seems to be falling apart, like the homework thing, and people aren't showing up, let me know. Like I was looking through the reviews of the classes last semester, and they said like, oh, people didn't do anything, and they got a 50 anyway on the homework, and it wasn't fair, and like, so I feel like it's not fair. Let me know. I mean, you have to turn someone in though, I think. So it's kind of, and it's a rotating group thing, so hopefully it won't be a permanent situation. I don't know. Anyway, if that comes up, so it will definitely come up, and then I'm not sure how to deal with it. I don't really think, like, you're all like upper level undergrads or grads, and the grades don't really matter at this point that much, even though you think they do. But basically, at this point, you've kind of committed whatever grade damage you're going to do. It's like you should be like harvesting A's now, like to just kind of boost it up. But so that's the way I see it. So and then I guess some people would be happy with a B. So if you get more than like 4 complaints or something, maybe they'll give you a B, you know, if you're undergrad, something like that. But it's not going to kill you. I mean, so anyway, so that's kind of where this thing sits. So editing is a good thing. All right, so that's a picture. So it's, and this is all pretty vague to you. So anyway, so the first thing I usually do in here is like say, go through like the different kind, like what is a polymer type thing. So anyway, this is a chemist's view of what is a polymer, and these are all the commercial polymers. You know, basically from a, what book this is, but the books. Okay, wait, sorry, one other thing. So there's a bunch of books. Let's see. So we got inside, not this, sorry. Inside here says books. So down here is a bunch of books. So the book I like is a Strobel book. So all the books are here. So you can kind of like click on that, but you have to go to the end of this and put in an F for PDF, and then the link will work. You know, so it's kind of like a secret password. So anyway, Strobel's book is here. So this is like kind of a high level book. So you might get shocked if you read that book. He's a German physicist, physical chemist, I guess. These 2 guys are American. So Colby's at Penn State, Rubenstein is at North Carolina. So you see there's like a missing F in this name. So anyway, this is like the current book that people are using mostly. And it follows the class pretty well. So you can see like, if you like isolated chain is one, and then somewhere it gets to be excluded volumes like crowded chains, some other things, Floyd-Huggins equation, some stuff, you know. So then he goes a lot into gelation things in here. So this is a pretty, I mean, you might find this book really challenging, but this is like an easy to read book, actually. And then Doy's book. So Doy was a guy, Doy and Edwards kind of wrote the theory of polymer reptation, which is like a complicated mathematical thing that's not readable. Then Doy, I guess, to make up for that, he published this little book. It's like a little teeny book. It's supposed to be for the complete idiot kind of thing. So it's also very difficult. And he doesn't use a lot of words, and you have to like really read through like what every equation he gives, like where did it come from, type thing. So it's a short book. It's a pretty good book. I mean, I've used it, but basically that's a pretty good book to learn the subject from. And then this Heimitz is like a really good kind of book for that was actually the first book I had for polymers. Was this time it's like 84 or something, I think. Polymer chemistry. He's dead now, I think. And then there's a new edition that came out that's written with a guy from Northwestern. It's a lot more stuff in it, but not as good type thing. So like the original one might be better. Because all these books though follow exactly the Florey's book, Polymer Chemistry from 1960, 60 something, right? So basically you'll see like it starts out with, if you look at this book and you look at Florey's book, so there's a lot of books, and somewhere is Florey's book in here somewhere. Oh, Joel Fried, also from chemical engineering at UC, also wrote a book. This is a pretty good book. It's more of like an engineering book. He was a chemical engineer. So he's still around, but he kind of moved on. He went to Louisville to be like dean of engineering, and then he's editor of something. But that's the book. But I think the book itself, yeah, the book's here. So Florey 1 is the original polymer science book, you know. So and basically all the polymer classes are based on this thing. I don't know what year it was. It was in the 60s. Don't say here, but yeah, principle of polymer chemistry. So anyway, you might want to glance at that too, especially if you're a grad student. And it's interesting to read it from a historical perspective because all the other books, so you can glance through this book, even just look at the titles of the sections, and go to every other book on polymer science, and they just copied this. You know, so anyway, Florey also himself copied a book. The book he won the Nobel Prize for, he copied from a Russian. So it's kind of like what goes around comes around, I guess. You know, so the Florey's books are in here. At the time, all right, so Florey spoke fluent Russian. And at the time during the Cold War, no one spoke Russian in the US in science, you know. So anyway, he had this heads up, like a couple of years heads up on this book, and he published the same book like 2 or 3 years later. Then a couple of years after that, he won the Nobel Prize for it. So anyway, so that's how the story goes. So there are a lot of books in here. For Tamara Gugas is a pretty good polymer extrusion processing book. It's old, but good. I don't know, there's a bunch of books in here to look at, you know, if you want. Nothing that notable that I can see right here, but also, yeah.
What is the main difference between the book from 1960 with the Florey compared to like the newer versions?
It's more readable. Like the Heimitz one's much more readable. Like Heimitz, you can, I mean, for me, all right, everyone has a different opinion about readable. But Heimitz, like when I first saw it, I could pick it up and read the whole thing without any problem. And it's very clear and he explained everything and like with a lot of insight, so you can just pick up what's going on. Florey, on the hand, it's like more challenging, I think, in a sense. So it might just be that in the 60s, people didn't care if you understood or not. You know, and by the time when you got to the 80s and 90s, when Heimitz wrote that book, I guess 84, it was getting into this age of like really almost like starting to think about spoon feeding type thing. Now we're kind of well into the spoon feeding generation. You know, so it's kind of like if you go back in books, they get harder and harder. Is what it comes down to. But if you read them and understand them, then you know more from those books than you know from a book that's kind of more spoon-fed type. So it's kind of oh, this book is really good too. Grossberg is another guy. He's a Russian, but in the U.S. So he interviewed here for a position in the physics department. You know, and he gave like 3 or 4 lectures, and then like they didn't take him. You know, and then he went to Harvard. You know, so it's like he's at Harvard now. So it's like anyway. So this book, this is his version of the Doi book, like a spoon-fed book for popular whatever. But this is actually a pretty good book. Like some of the things he goes through, particularly like chain collapse, like in protein folding and DNA stuff in here, like the best anywhere that you can find it because it's so simple. This is spoon-fed, but it's like without spoon feeding that, you wouldn't have any idea what's going on. So it's kind of like pretty useful book to look at. And it's meant as easy reading, and you'll notice it'll go through exactly the same subjects. It's just like a little bit different approach to it. So I think that's a pretty good book too. So there's a lot of books. I mean, if you want to, so there's plenty of books here for you to look at if you want. Anyway, so that's they're all here. So the Colby one, like download that one right away, and then I'm gonna kill the link to it or change it somehow. Because that one has gotten to be on the internet somewhere. So I don't want it to be like search to because I know those guys. So it's gonna like the internet. So anyway. So it's there for it's there a kind of limited term engagement. The other ones, I don't think anybody cares about, as far as I know. So anyway, so let's see, what we got on time here? A couple minutes. So, all right. So basically, yeah, the chemists, that's what they see. So you have like polystyrene. So you have the vinyl polymers, 2 carbons and some side group on it. So this basically, if this is a hydrogen, that's polyethylene, right? And then if that's N is 12, that's wax, right? And then N is 100, that's polyethylene. It's like wax and polyethylene are the same thing. It's just different molecular weights, right? So in fact, you can look at it like you look at the melting points. So these are the alkanes, meaning that polyethylenes like carbon, carbon, carbon chains. So one is methane, right? And this is the boiling point of methane, is like some low temperature. And this is where it crystallizes. Methane, I don't think it really crystallizes. I guess at some point it does. Then ethane, propane, butane, pentane, whatever. Hexane, heptane, hexane, heptane, octane, nonane, whatever. So you're up to like 10 around here. And then it doesn't boil anymore at some point, right? So that's like waxes don't exactly boil. I mean, high molecular weight, or squalene is actually from sharks. It's a alkane of 100. So it's used as a prototype of polyethylene. Squalene actually has double bonds in it, but they hydrogenate it, and then they use it as a monodispersed polyethylene kind of from sharks. But anyway, so this is going to be like squalene somewhere here, and you notice like this thing kind of acts weird. Like you have like a liquid, and then all of a sudden it just the melting point goes up, and the jogging of this thing is because the polyethylene chains, when they crystallize, they line up like that, and then when it's an odd number, they like have to jog to fit the N group in. And when it's even number, they fit at even. It's basically this jogging that happens is because you're going like odd, even, and the crystal form has to change a little bit. And then they form sheet crystals. That's why wax is like waxy, like it's lubricant. Like you can use wax to like grease a door or something if you want, because it makes these sheets like graphite's the same way. Anything's like a sheet structure is going to be like a lubricant, right? So anyway, so it forms a sheet, and at some point, like something happens, and then the melting point doesn't change anymore. So you can see that as you're going up in the molecular weight, so the crystals are getting to be thicker because they're longer chains, right? And the thickness of the crystal has something to do with the melting point, right? In fact, the longer the crystal, the higher the melting point, right? So then basically something happens here where it doesn't change anymore. So you can say, well, that's because the crystals don't change thickness anymore. So they've reached some kind of a point where they're not going to get thicker as it gets longer. Like if you have a 10,000 molecular weight or 100,000 molecular weight polyethylene, it's not going to make 100,000 crystal. For one thing, they aren't all of the same length. They're a variable length, right? So they can't all fit into that crystal structure. And for another things, these things are like kind of like cooked spaghetti. So like you think about, well, if it's a short cooked spaghetti, they can kind of fit together and crystallize. But when it gets to be long, they flop over, right? So it can't do that anymore. It can't like make these long chains. So at some point it reaches this flopping over point. And that turns out to be just related to the enthalpy of melting of the crystal in the surface energy for the full surface, which is a high energy. It's like when you have an alkane chain, you do a hairpin turn on it. That's a lot of energy. It's got a really high energy. That means it's got a fixed thickness. It's going to be about like 100 angstrom, 10 nanometers thick. So it's a nanocrystal, right? And then substantial amounts of this chain aren't going to fit into that crystal for whatever reason. It could be kinetics. It's also, if they have random branches on them, like high density polyethylene, the branch points are going to be excluded, right? Or if you intentionally put in short chain branches, like in low density polyethylene, then you select the crystal thickness by the spacing of those branches. And that in turn selects the melting point of the thing. Right. So you can see like, these are things like when this plateaus over, these are like useful thermoplastics. And the stuff down here is wax. So you wouldn't use wax to make a milk jug because it would fall apart. You can wax coat paper, or you can polyethylene coat paper, but you don't use wax to make structural elements usually, right? Because it just falls apart. Also, it melts at too low of a temperature, so your whole milk jug would melt when it got warm out, right? So it wouldn't be a good thing, or would sag. Right. So anyway, so the thing's going to have this feature of a constant melting point with the chains once you get to this thermoplastic regime. So you can kind of look at it in terms of crystallization behavior defines what a polymer is. Like when you get above 100 times, I think it's like 72 for polyethylene, so 7,200 molecular weight grams per mole, then that's going to be a polymer. And below that, it's going to be what's called an oligomer, which would be wax. Right. So every polymer has this feature that there's a transition point about 100 in terms of units, like polymerized units, which are like the chemist things, these things. So if the R is H, it's polyethylene. If it's methyl, that's polypropylene. It's like 3 carbons. So propylene would be like a double bond. Propene is a double bond and then a single bond. And then it opens up to make the chain. You see on this methyl group on the side. And then if you put an aromatic group, that's polystyrene, Cl's polyvinyl chloride. And then acetate, put an acetate group on it. Put a hydroxyl group is vinyl alcohol. So this thing's called vinyl when you have a double bond opens. That's your vinyl polymers. Usually vinyl refers to PVC. But basically, these are all vinyl polymers, right? So you can, along that motif, you can put like anything you want on the side of it, right? Or you can kind of double, you put 2 R's on the side, right? So that this kind of olefin-based chemistry is pretty broadly scoped. And then there's other condensation polymers will have, this would start with a dialcohol. So what's that called? Glycerol, I guess. The 2 OHs on the end of ethylenes. And this is dicarboxylic acid, so it's got an OH and an O and a double bond O, and then that condenses to water, comes off. The OH and the 2 OHs give off the water and with an ether kind of link here. Right. So that's pretty typical condensation polymer. So if you can drive the water off, like boil it or something, you can drive this polymerization because you have get rid of the product, you can drive the reaction, you make this a long polymer. Right. So all the polyesters, which would be like this kind of ester link in it, and then this is a polyamide. So it kind of looks like proteins have that kind of structure. So anyway, these are all condensation, kind of giving off either water or HCl, some other kind of product like that, right? And then there's natural polymers like cellulose. Those are a little bit different synthetic routes, but right. So that's kind of an overview of some of the chemistries, right? So, or you can just say that this thing is just a chain, right? Just like there's some others, right? So you could just say, well, it's just a chain like this business, right? So anyway, you just go back to here because this will let me do it on time. Get some time. Believe it or not, the links I think don't work in the thing, but this link I want to look at. Worked yesterday. There. All right. So this is so basically let's see. I got my mask in case someone has COVID. Give me fair warning. Alright, so if you set up a, let's see, is this guy gonna do that? It's on projector. Oh, no, that's what I'm saying. Let's see. Doc cam on projector. Doesn't want to let me do it. Let's see, projects. Doc cam, project. All right, good. All right, so if you typically people will like set up a grid, so a Cartesian grid in 3D. That's kind of right. So you set up a grid, right? So you gotta, so it'd be like, so basically you have like X, Y, Z. So you gotta say, you start at some point like 0, 0, 0. And then you're gonna take like a step, right? So take a step to here, so it'll be like, if that's Z, it's 0, 0, 1. Right, so you've taken the step. So basically you could do that in several different ways. So you could do it like say I'm going to do it in a 2D grid, or say I'm going to do it in a 1D grid. So I say I'm going to just take straight steps. So I'm going to go step, 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 step. Then I'd have like the length of the final thing that I made, and then how many steps I took, Z or N. Right, and I'd say, well, and each step has a length of L. So the length final thing is like this L times M. That's the size of the thing. It's a rod. It's the size L times M. I just took straight steps. Right? So you could say like R by L equals N, and there's some kind of number here, which is 1. So it's called a 1D object that you make. And if you had a 2D grid, and you could say, well, I'm going to do like a raster on this. I'm going to go up to here. I'm going to go back and raster there. Then I'm going to go back and raster here, back and raster there. So I'm going to end up with something like that. And if it's evenly spaced, then I end up with R by L. It's going to go with this, kind of the distance of this thing. In the end, it's going to be like n to the 1/2. R by L squared is, so that's 2D. I guess capital D is better than 1. And if I did that in 3D, so I rastered one thing and I did the next one up, the next one up, the next one up, right? Then I build up a 3D object. And that thing cubed is how many things are. Like if it's a 10, there's going to be 1,000 steps I took to make it. If it's 10 here, it would be like 100 steps, and this is just 10 steps. But that's one way to make things. And these are called, this is called regular objects. Because they're dense, like dense objects. And if I take one of those objects like a cube, then I'm gonna like take one point here and I'm gonna run electric current through it, and it's gonna go to the other side. That follows a straight line. So that straight line is a definition of a regular object. Right. Take that and compare it with like something like a dust bunny, right, which is gonna be some kind of thing like this. Well, then, if you take the point here and then you're going to find a path through it, it's not going to be a straight line. It's going to be some other different thing. Right? In fact, you could take that thing alone, and it would be a thing that looks like that. And so that's called a linear path. And that thing has some other dimension, fractal dimension. Right, so you have kind of regular objects and these kind of things. So polymers are well within this category of things called fractals. It's an example of a fractal, and the kind of prototypical polymer is going to be a linear chain. They call it a linear chain, even though it isn't a straight line. Linear because there are many branches. It's not a 3D object. It's not a regular object. It's some kind of odd looking thing like a fluff piece of dust or something. So if you think about that, then you can kind of so if you if you do this grid thing again, if you do the grid thing again, then to do the polymer, you're going to do this. I'm going to start at 0, 0, 0. And you're going to say flip a coin for the sides of it and say heads or tails. if I go left or right, or flip a random number, it's gonna give me like A, B, C, D, E, F. I can go any of those 6 directions, Cartesian directions. I'm just gonna randomly pick that. So I'm gonna pick a number between 1 and 6. If it's 6, I'm gonna go down. And if it's 5, I'm gonna go left. And if it's 4, I'm gonna go in, 5, whatever, in, out, whatever. So you're just doing a random number. So then you're gonna make something different than this. Make something different than when we did this kind of grass string thing. We're gonna make. So that's how you would construct a dust bun, say, or a fractal. A linear polymer is gonna be a linear walk. So you can go like random choice, go here, random choice, go there, random choice, go here. And then you find out that this is just like the problem for diffusion, like when you do diffusion. Like when you, so for diffusion, the distance you travel, so this R squared divided by time at a constant velocity. So velocity times time is that step length, kind of. That's going to be the 2 times the diffusion coefficient. Right, so you have kind of the distance, this R squared for diffusion is 2 times the diffusion coefficient times time. Right. So it's this thing squared. So basically, this thing, that diffusion path is a 2D object. Because you have, if T is like the mass, then this thing is like the square root of the mass because you have this distance you travel. So if you plot it out, diffusion paths, then you expect this kind of thing. So expect to see that the thing's going to follow this Gaussian E minus R squared. So if you plot out versus distance over 2 sigma squared, right? 2 or 3/2 sigma squared, which is in 3D. This is going to make, that's a bell-shaped curve. So you have basically R squared, so it's the same going forward and backward, because the square of a negative is a positive. So it's the same forward and backwards. And then this is the lowest order if you do that. And then it's got to decay to 0 when we reach the total number of steps, so n times L. So it should go to 0. The exponential doesn't exactly go to 0, so it's an approximation. Right, and then at the maximum position that you reach in the diffusion path is the origin. So if you just say, I'm gonna throw like dye into water, and I'm gonna let it diffuse out. Right, well, it's gonna follow that path, and the place where I'm gonna find the most dye is where I put it, like right in the middle. It's 0, 0, 0. That's where it goes to begin with. Right, so if you're constructing these polymer chains, there's an exact analogy to this kind of diffusion. So this is called a diffusive path, Brownian motion, the Brownian path. There's a lot of different words for this. So you can take like one, I'm not sure what the particle thing is here, but number of steps, that's kind of obvious. You can do 100 steps and then do a walk. And then the 2D walk is a picture of it. Right? So if you do it again, it flips. I guess you have to keep clicking. So if you do, oh, sorry. Yeah, it's good. All right. So this goes to 30, so we want to get this larger than 100, so make it like 1,000.
It's still coming.
I should do PC on projector. I think there's like a delay in this thing. Actually, it's a demonstrated delay. And it doesn't seem to, all right, I'm gonna have to call the guys, I guess, at some point. That thing's on projector, PC. It made a noise, right? I heard something happen. Nice if this guy would show up. Could use my computer, I guess. I wonder if this thing works. None of them work. This guy's connected, it beeps too, so it's not a good sign. Oh wait, it did go to that eventually. It's like it takes a while. I should have just actually waited for that guy. Just gonna show time to show. Maybe it goes back there. Okay, good. So, here. So here, just do walk 1D. So this is a path that it took, and it's a 2D. Sorry, there. So this is just a 2D grid on the walk that it did for 1,000, 2,000. Right, push the wrong button. So anyway, you can get a bunch of these. You notice that every time you do it, it's a completely different thing, right? So there isn't any one, but you can't say, I mean, like ethylene, you can say it's this rigid structure, you can draw a picture of it. This thing, you can't draw a picture of one of them. Like they're all different, right? So there's the statistics involved in it. It's just like a Brownian path. And if you say, if you do like 100 of them, so they all will center around the center, right? So the idea is like everything's piled up in the middle. The average place where it's going to end up is 0. And it's got some kind of average structure. So the only way to describe this thing is by using the average of R squared, the average of some even power, because it's going in either directions. It has to be a square or 4 or 6. Basically, the first thing is this sigma squared, the standard deviation. You're just going to be like kind of right about in there. That's the average size of it. So they don't have a real size. They have like an average size. Right, so it's this average R squared. And basically the distribution for those walks, I think it calculates every time you click on this, is going to be this Gaussian peak thing. 2,000. I did this for 10,000. Do 500 or something. Oh, there, right. They got the variance. So this is showing the average value goes with time. So the average squared value or average sigma squared. So the size of the thing goes with time to the 1/2. So it's going to be like, basically this is going to be like end of the 1/2. And the distribution function, what does that say? Oh, in or less than 2,000. Seems to be less than 2,000. Anyway, the distribution function will be a bell-shaped curve. We're out of time anyway. So yeah, so if you want to play around with that, you can kind of see that it ends up being a bell-shaped curve. So anyway, so I'll see you on Wednesday.
The fusion of polymers, was that with those charts?
It could be, but no, this is actually making a chain. So you don't like a step to step.
Oh, okay, with
But the
where,
path,
yeah.
the path of the chain follows the diffusion.
Oh, yeah.
So it's the same thing as diffusion.
Oh, yeah.
Yeah, but actually, if you watch a polymer diffuse, it'll follow the same path. So it's like 3 things. I guess.
Oh, yeah. I just wanted to make sure.
All right, yeah, thank you.
Well, like, you know, it's okay, they don't want to be.